Good day, I'm Victor Salanga and my design project is a wireless temperature transmitter. Temperature sensing is a vital process in our daily lives. In order to monitor one's well-being, temperature sensing is being utilized to be able to detect if a person is sick or not. This is especially useful in today's time where a global pandemic crisis is happening. Furthermore, temperature sensing is not only limited for human uses. It can also be employed through different mechanical and electrical purposes. For equipment or places that are dangerous or inaccessible to people, temperature transmitters may prove reliable and essential in order to measure and monitor its condition. The information it obtains will then be sent through a receiver station to process and interpret it, conveying reliable and useful information. The goal of this design project is to provide a teardown of a wireless temperature transmitter. It also aims to provide a detailed analysis about its components and its respective functionality. First, let us choose a temperature sensor. There are different types of temperature sensors available in the market. It could be a resistor temperature detector, a thermocouple, a semiconductor sensor, or a thermistor. For this project, we will use a semiconductor sensor, which is the TMP36 low voltage temperature sensor. The TMP36 sensor can detect temperature from -40 degrees Celsius up to 125 degrees Celsius, converting it to an output voltage. As you can see in the figure, the TMP36 is powered by a battery, then it detects the temperature. The temperature is now converted into voltage, which is read by a voltmeter. But how did the temperature get converted to voltage? The answer lies within the sensor's internal circuit. As you can see in the figure, the core of the TMP36 sensor is a bandgap core that comprises transistors Q1 and Q2, biased by Q3 to approximately 8 microamperes. The bandgap core operates both Q1 and Q2 at the same collector current level. However, because the emitter area of Q1 is 10 times that of Q2, the VBE of Q1 and the VBE of Q2 are not equal. This is shown in the displayed equation. Resistors R1 and R2 are used to scale the result in the displayed equation to produce the output voltage transfer characteristic of the sensor. And, simultaneously, R2 and R2 are used to scale the VBE of Q1 as an offset term in Vout. The output voltage of the temperature sensor is available at the emitter of Q4, which buffers the bandgap core and provides load current drive. The current gain of Q4 working with the available base current drive from the previous stage sets the short circuit current limit of the device to 250 microamperes. Now that I've explained how the TMP36 sensor works, let's set it up for testing. The schematic diagram for it with all the necessary components is shown in the figure. I assembled the circuit in Tinkercad and the output is shown in the figure. As you can see, the temperature had been converted by the TMP36 to produce the 48.3 mV displayed by the voltmeter. By changing the temperature detected by the sensor, the voltage read also changes accordingly. When we set the temperature to -40 degrees Celsius, the voltage read is 60.44 mV. When we set the temperature to 125 degrees Celsius, the voltage read is 113 mV. These will be the transmitter's configured output voltage limits. Now that we saw our sensor works, let us build the wireless temperature transmitter. Shown here is the black diagram. First, the temperature is measured. Then, the transmitter outputs a voltage. After that, the receiver detects the voltage. Next, the voltage is converted to temperature in degrees Celsius. And finally, the temperature in degrees Celsius is displayed as voltage. The transmitter is already built earlier and is shown here is the circuit I built in Tinkercad. To process the output voltage from it, we will need a receiver. For the receiver block, I designed it to have 3 operational amplifiers. The first one is a differential amplifier that subtracts 6.4 mV from the transmitter's output voltage. The output from it will enter the second one, which is a non-inverting amplifier That multiplies it to a gain equivalent to the slope of the transmitter detected temperature and voltage output, which is 1.547. The output from it will enter the third and final one, which is another differential amplifier that subtracts 40 mV from it. The output from it is the actual detected temperature by the transmitter, which is displayed in volts that will be read by the voltmeter. Now that the receiver block is done, the wireless temperature transmitter is complete. Shown here is the complete schematic diagram of the transmitter and the receiver. I assembled the circuit in Tinkercad and the output is shown in the figure. As you can see, the temperature had been converted by the TMP36 to produce the 48.1 mV displayed by the first voltmeter. The second voltmeter reading is 25.7 mV, which means that the actual detected temperature is 25.7 degrees Celsius. By changing the temperature detected by the sensor, the voltage read also changes accordingly. When we set the temperature to negative 40 degrees Celsius, the first voltage reading is 6.41 mV, while the second one is negative 38.7 mV. It may have skewed a little bit due to stray impedances. When we set the temperature to 125 degrees Celsius, the first voltage reading is 112 mV, while the second one is 125 mV. It is pretty accurate this time. That is my design wireless temperature transmitter. The wireless temperature transmitter had been analyzed and dissected through its components and functionality. The sensor used is the TMP36 low voltage temperature sensor. Its circuitry makeup and incorporated components had been tackled and explained. The receiver block had also been given focus. The sections incorporated to it, such as the differential and non-inverting amplifiers, had been elaborated to give a perspective regarding the system's operation. Through the teardown of this design project, it can be inferred that commercially available wireless temperature transmitters in the market operate similarly, if not purely identical, to the electronic circuit discussed here. Taking everything into account, the goals of this design project had been met for the teardown of a wireless temperature transmitter. That concludes my presentation. Thank you very much for listening.